Guess we'll start. So good morning, everybody. So today we'll be talking about the fundamentals of microfluidics. And the goal of this 2-hour session is to sort of introduce you to sort of the basics of microfluidics. This is a very basic course. It's not aimed to present very advanced concept. The idea is to present sort of the basics, where you won't be going out after this course and designing all sorts of microfluidic systems, although some of you do, as part of your daily life. But it's sort of to give an overview of what's out there. And so when people talk about these systems, oh, okay, I understand what's going on. I understand how these things work. So to begin, I'll do a little demo, but before I'll ask you a few questions. So first of all, does everybody can hear me in the back? Awesome, awesome. Okay, I'll try not to use this mic because I have way too many things in my hands. So if you guys can hear me in the back, I'll just speak loud. So just to get a show of hands. So how many had coffee this morning? Okay, very many people. Okay, when you have your coffee, do you guys mix anything into it, like creamer or something like that? Yeah. Okay. So when you mix the creamer, have you ever tried to unmix the creamer? Like you mix it, it's all like mixed up, and you try to unmix it. Okay. Anybody succeeded in unmixing creamer from their coffee? Okay, you have. Oh wow. Okay. All right. Anita can do magic. Milo apparently. Magic. Okay. All right. It's a fairly difficult thing to do, especially at micro scale. So I'll tell you why that is. So we live. Normally, we're kind of big, I guess, and we live in a world that's dominated by inertia. So when we swim, when we drive our car, when we swim, we throw water backwards, and that's how it propels us forwards. When we fly in an airplane, the airplane engines throw air backwards, that propels the airplane forwards. Same thing with rockets, they throw hot gas backwards. The giant rocket moves forward. But in microscale, interestingly, inertia doesn't matter. So it matters much less than viscous forces. And in everyday life, it's almost impossible to witness that. That's kind of highly weird phenomena. So what I'm trying to do today is I'm going to try to immerse you take you from this inertial world that you live in all the time to this viscous world that you'd find in microfluidics. So what happens as you scale things down, bodies become smaller, and so their inertia matters less and less. And it turns out the viscosity of the fluid matters more and more. And so the way I'm going to do this, and the way people do this, is that I'm going to do a scaling model. So normally when you want to examine an airplane, for example, you don't take a 787 and stick it into a wind tunnel. There are very few wind tunnels in the world that's capable of doing that. What you do is you take that wind tunnel, you take the airplane, and you think, what are the relevant forces on that airplane? Okay, so for example, the relevant forces in an airplane might be the ratio of inertia to viscous forces. So that's the Reynolds number. Try. Right. So the Reynolds number is the ratio of inertial forces to viscous forces. So if you can see that if you have a lot of density, you're very dense, then you intuitively have a lot of inertia. If you have a lot of velocity, you would have a lot of inertia. And if you are big, you'd have a lot of inertia. But if you're in a fluid that's highly viscous, the viscous forces will be dominating upon you. So there's a trade-off. And so the way to do this is to, to kind of place you in a world that's very viscous rather than inertial, is keeping the length scales the same, so you guys can see this without microscopes or anything like this, is to use, instead of coffee, which is mostly water, a liquid that has very high viscosity. So that's exactly what I'm going to do today. So I'm going to use this corn syrup. So right out of the grocery store, just usual corn syrup. So this has viscosity about 2,000 times that of water. So it's basically, if you take this Reynolds number, the length scales are the same. The density of this liquid is about the same as water. The velocities, well, I'm going to have to go a little bit slower velocity, but by putting this viscosity to be much higher than a water, I'm dropping the Reynolds number and taking you from an inertial dominated world to a viscous dominated world. So we'll see what happens. So I'll do this in this little apparatus. It's nothing more than just a little cylinder and another cylinder together, so that makes sort of mixing things a lot easier and a lot cleaner. And so we'll see what happens. So just to show that there's no tricks, it's an empty cylinder right now.
Every magician says that too.
Exactly, I know. And so I'm going to pour this corn syrup into this. Okay. Sort of to visualize the mixing, instead of like creamer, I'm going to use something a little bit better. I'm going to just use this dye, fluorescein dye. It's a very, very simple dye. It's actually very benign. People get this injected into their eyes for certain visualizations. They dye rivers with this, like I think on St. Patrick's Day, they dye the Chicago River with this. So very safe dye. And the nice part of it, it's very green, and when you put it under some light, especially blue light, and this is kind of a blue light, bluish light, it'll fluoresce green, so it gives off a green color, and it's easy to visualize. So we'll try to dim the lights maybe so that people in the back can kind of see this. We'll see how that goes. If not, you'll see it on the video. So I'm going to try to inject a little bit of this dye syrup in here. So let's see after the bubbles are gone. Can anybody see the green coloring? Green dot here? Just the front rows. Let's see if, I'll try to raise it up so maybe you guys can see it sort of in the back. Can you guys see it in the back? Like a very nice green dot? Kind of? Okay. So then I'm going to do some mixing. Okay. That's not going to work. Yeah, if you can help me. Thank you.
Just hold that.
Thank you.
Maybe you should from the side.
Yeah, is that better? Top?
Yeah.
All right. Okay, so now it's mixing. Mixed all the way. Okay. So now we'll go back. Pay attention to this. And now I unmixed it. Right? Okay, so let me do this again. this is it mixed. You can see the band. Now it's a band. It used to be a dot. Now it's a band. Okay. And now it's completely unmixed. That's a pretty weird result, right?
Was it really mixed or it was just spread?
Well, that's a good question. Right. So was it mixed or was it actually spread? That's a good question. Right. And so why can I do this? Why can I take it, spread it, right? And then unmix it, or just put it back in its own place. So why do you think I can do this in a viscous flow, but you cannot do this in an inertially controlled flow, like in your coffee cup? Anyone has a guess?
Diffusion.
It has to do with diffusion. So diffusion, there isn't much diffusion here. And actually, if you let it sit in the coffee cup, there isn't that much diffusion. You can see the time scales. It's like, it took me about a minute to do this. So it wasn't a very long time. We didn't let it sit in for a long time scale. And so diffusion does play a role, but why do you think this is? Yeah?
Well, in an inertial-driven system, once you've stopped mixing, the mixing continues. And so that can't be reversed by reversing the mixing.
Absolutely right, yeah. So basically what happens in an inertial system, just to basically repeat what you said, is you push the fluid with the boundaries, and the fluid just continues, keeps going. And so that there's no way you can control back by turning the boundaries back where the liquid starts out from. And so in your coffee cup, in your stirred coffee cup, actually the Reynolds numbers can be surprisingly high. So basically the Reynolds number, you take density of water, about a 10 centimeter diameter coffee cup, and you're spinning it at 10 centimeters a second. So you're moving one diameter in a second. This is for water. This becomes actually turbulent. So it's highly inertial driven, and you have this effect just like you mentioned, where the water or the fluid keeps going. In the corn syrup demonstration, the Reynolds number is much slower, and so what happens is that you actually have these lamina, and when you tug on one of the boundaries, these lamina move, right? And once the lamina move, basically what it looks like as it's spread. So Pavel was right. It's not actually mixing. It's actually just shearing it. I'm just shearing on the lamina. And then, because there is no inertia, so these lamina don't go anywhere, like you mentioned, I can take the walls and move them back, and the lamina come back again. So it's very unusual in our macro scale world. It's very, very usual in this kind of behavior in the micro scale world. So if we actually scale this would be, if we scale this appropriately, that I'm going basically a few turns on this device in a time I'm doing this, this would be roughly a 100 micron sized device. So instead of 10 centimeters, it'll be a 100 microns type device. You would see this kind of behavior. And this kind of behavior where the boundaries only cause the movement of the fluid and there's no additional inertia has significant influences on what's actually going on. So for example, if you design a micro swimmer, or think about how cells swim, because they're so small, they cannot swim the way you swim. So if you're trying to push water and try to throw yourself forwards, by throwing water backwards, basically what the little bacteria would experience if they would do that, they would just come back. They would go forward and then come back. Go forward and come back. It wouldn't do anything good to them. They wouldn't actually be able to move around. So it has to be special asymmetric motion that these little microorganisms have to do to actually propel themselves forward. For example, if you are in a boat, you can move your rudder back and forth like this, and you'll be able to move forward in the boat. If you do this, if bacteria does this, it will not actually move anywhere, it will just churn water around it. So it has significant implications. And so this is just a flavor of the weird world that you'd find when you're dealing with viscous dominated fluids. Okay? So, any questions about this? So, next I'm going to talk about, having this sort of introduction, I'm going to talk about the second part. So I'm going to talk about So I'm going to talk about the various common subfields of microfluidics. So there are a few things that I left off. So I mentioned centrifugal-driven microfluidics. I mentioned inertial-driven microfluidics, capillary-driven droplet microfluidics, and electrokinetic microfluidics. There's a few other subfields of microfluidics that I do not mention here, but just for the sake of time. For example, there's also pneumatic-driven microfluidics, and they work as you imagine. You take air and you put air to drive liquid inside little channels, and if you want to actuate a valve, you have a membrane that you put pressure, air pressure on one side, that depresses that membrane and closes off a channel. So that's basically the other major microfluidic that I left off. But these are different microfluidic methods, and kind of wanted to give you a brief overview of each of them and how they work. So the first one is centrifugal microfluidics. So around the 90s, when the CDs began to be kind of popular, there was an idea that, well, we have these nice CD-ROMs, they're everywhere. They have precision mechanics, so they can spin this disc very precise speed. They can stop, they can start. In addition, they also have this very nice laser and fairly nice optics, so they can do at least some sort of readout, And it's all there, it's all very cheap, it's already in many people's computers. So if we're going to do a lab on a chip, we want to make it democratized, why not do it right on your CD player? And so what they came up with is taking a disc, just like the same size and shape of your CD, some sort of plastic, and putting channels in these discs, and filling these with some reagents, some of these reservoirs with reagents, and using the centrifugal forces, so where the force is proportional to the rotation and the velocity squared, so and inversely proportional to the radius, and also proportional to the density and the volume of the what you're trying to move in this disk, and use this kind of force to move around objects. So the nice part of these disks is that it basically mimics what you would do on a normal laboratory centrifuge, right? You'd use normal laboratory centrifuge to separate out things by density, right? Because things of different densities experience a different force. And so, for example, if you take blood, it contains cells that are denser than the liquid. You put them in such a device. For example, here you put a layer of blood. You put a centrifugal force on this by spinning this, and you would get cellular pellet and a plasma above it, as you would expect in a normal centrifuge. And by creating, like this interesting structure here, where as you are flowing more into this chamber, the top overflows and fills into this chamber, and you can do density separations, just like you would in a centrifuge, except with minimal effort and fairly nicely automated. So that showed a lot of promise, but it turns out nobody trusted putting these kind of liquids and these disks inside of their own machines. I guess there was some sort of aversion to this, breaking your very expensive computer. But what happened is you could still leverage the mechanics, the cheap mechanics that are developed for these mass-produced CD players and also the readout, and build these kind of boxes, standalone boxes, to do this analysis. And there's a few companies out there who actually manufacture these boxes and sell tests based on this. So this was the result of lab on the CD. And so the advantages of this, as I said, is that you can mimic traditional operations that you would do in a laboratory, so there is much less development that you have to do. You can just take the kits that are already there, and you can just implement them in this nice, fairly automated fashion. And again, you can reuse the parts from this industry. However, there are significant drawbacks to this. Is that, first of all, once you spin this disc, and everything has to move from the inside to the outside, right? Because the centrifugal force you can only apply to the inside to the outside. That's the only thing you can do. And the other thing you can do is that you can spin up the disc, so increase the RPMs, or slow down the disc. And so you can only increase or decrease the force. So once you increase the force, and for example, you increase the force, you put some force on a fluid, and you had a capillary barrier valve, so a valve that's being held back by surface tension. Once you broke that, you cannot go back. So most of these operations are completely irreversible. So it's basically you're designing a system that can go only in a single direction, and that makes it relatively difficult to use and to design around. And so this is sort of the main limitation of these devices. The second main limitation of these devices is that the instrument readout is fairly difficult. So for example, you're spinning this disc. You're spinning this, and you don't have normally electrical contacts on this disc, right? So if you want to do traditional electrochemical readout, that's fairly difficult to do. You have to have some sort of brushes or some sort of mechanism to contact electrically to a spinning object. Normally, you just put electrodes on a chip and you're done. So that makes it a lot harder. And if you want to have a lot of electrodes, you have to have a lot of brushes, and that makes it exceedingly difficult, especially when one of them loses contact, right, in your device. Secondly, if you want to do optical readout, that's a little bit better. That's not as bad as electrical readout, but still you have to stop the disc, and you have to stop the disc or time your optical system to take data at appropriate points. And although it's somewhat figured out by the CD and then DVD community how to do this, it's still fairly difficult if you want to have, for example, long exposures. You cannot do this because the disc is spinning, or you have to time and position the disc. So these are sort of the drawbacks to this technology. So the next technology that's very popular in microfluidics is inertial microfluidics. And we actually, in TIJ, we practice some of the inertial microfluidics. The folks who do TIJ, they tell you that as the bubble expands, the Reynolds numbers are very high, instantaneous Reynolds numbers are very high, and so there is quite a basically you're inertially throwing fluid out of the nozzle. So here, Reynolds numbers are again also, even though the channels are small, the fluid flow is so fast that inertia is important. So in these devices, you just try to force the fluid to flow faster. And if, for example, if you have particles that are much denser than the fluid, the particles have certain inertia. So they experience several forces. So the first force they experience is wall lift. So you can imagine if you drag your hand through a fluid, you have this disturbance around your hand, right? When you drag your hand through like a pool or something like that. So same thing here, when you drag a particle through a fluid, it'll create a disturbance. And if you have a wall that's somewhere nearby this, that disturbance will push on the wall will push back, and that force will be transferred to this particle, right? So if you have this, the particle will experience a force away from the wall, and that's called the wall lift force. And in these microfluidic devices, it's slow flows. These disturbances can be quite far away from the actual particle. It can be as far as 10 diameters, and you still see a disturbance in the flow. And so even relatively far away from walls, you still see this wall lift force for particles. Okay? So the next force that's important is sedimentation force. And the sedimentation force is just basically the force of things falling to the ground, right? You have a gravity vector somewhere, and the particle has higher density maybe than the fluid, and so it will want to sediment out. There's net difference in these forces, between net difference in the densities, and so there's a sedimentation force. And the particle, of course, has lower density in the fluid. It'll have a opposite. You have a buoyancy force. So that's the force of sedimentation. And also, you have your usual Stokes drag. So if something is pushing the particle in this direction, right, there's a drag force that's proportional to its velocity, and also proportional to its radius and the viscosity of this fluid, okay, that it is in. And you can also combine this with a centrifugal force. So for example, if you arrange your channel in a sort of spiral pattern, what happens, just like in centrifugal microfluidics, the particle, like you're going around the corner, if it has more inertia, its inertia will want to keep it going in a straight line as it's going around, as the fluid is trying to take it around these turns. So it has its own centrifugal force on it, right? Because it's trying to go in a straight line, the fluid around it is going in a circle, so it's trying to go towards the wall. And that force on it, that centrifugal force on it, on this particle, will be, of course, opposed by this wall lift force, right? And so, in that sense, if you have those particles, you can separate the particles based on how well they experience the wall lift force versus how well they experience the centrifugal force. Because somewhere, these forces will balance out, they cancel, and so the particle does not experience any lateral motion in the channel, and it'll actually focus at some point in this channel. Okay? And if you have particles that experience different forces in this channel, you can use this to separate out particles, right? Based on this. So it's a very nice membrane-less, ideally does not foul. Of course, you know, in real world things stick to surfaces and there is some fouling, but in an ideal world this is pretty much a foulless filter that you can generate just by generating a particular microstructure, and by tuning the flow rates you can separate out particles and based on this. Okay? And in addition, another area of inertial microfluidics, another example of inertial microfluidics, is this pinched flow fractionation. So it works a little bit differently than the spiral microfluidics that I just showed you. But in here, what happens is that you still you have above two fluids, one that has your sample, okay, and you have a fluid that's clean. That's, for example, a buffer inlet that's clean of the particles. And what you're trying to do here is that by flowing the buffer at a certain rate relative to the sample inlet here, you try to push all these particles to this wall. Okay? And so the particles have different diameters, and once they hit this wall, their center of gravity, I guess, the center of mass, their center of mass will experience a different flow velocity, right? Because here, near the center, there's higher velocities, and directly at the wall, there's zero velocity because there's a no slip condition. Things don't move near the wall, and there is usually a parabolic velocity profile here. And so the velocity that acts on this particle translates to the drag force that it experiences. And so the particles in the center will try to, bigger particles that are experience forces near the center will follow streamlines that are next to the center. And the particles that are small will still keep trying to hug the streamlines that hug the wall. And through this, you can actually also separate out particles based on size with this also fairly simple contraption. Okay? And so with inertial microfluidics, you can separate particles based on their mechanical properties, such as their density, their deformability, and the deformability in their shape, their eventual shape, governs their lift force. So all the lift forces that I've shown you were for spherical particles, those little equations. So for different sized particles, there's slightly different lift forces, and they have scaling basically if the particle is an ellipsoid shape or a discoid shape, like a little blood cell, red blood cell, so a little disc shape. They'll have slightly different lift forces, and so you can separate them out as well as, of course, by size, which is the simplest out. And you can do this without having any mechanical filters, and this device will work without fouling in ideal situations. It's pretty cool. And you only need a single pump to operate this. So you don't need electric fields, you don't need any high motors to spin this as you do in centrifugal microfluidics. There's quite a bit of advantages to doing this. And you also do not need other forces to do this. So, but however, there are some disadvantages. Typically, the flow rates that you need to do both of this and the spiral, anything that has inertial microfluidics, inertial forces are high because you need to have relatively high Reynolds numbers. And so you would need to use high pressure parts and high pressure components, and that can become quickly very expensive. It depends on your design, how high a pressure is and how expensive it is, but if you make the channels really small, you need these very large HPLC pumps to do this. You also put these particles that particularly maybe cells or maybe macromolecules under particularly high shear, right? Because at the wall you have zero velocity, and in the center of the channel you have this high velocity to generate these high Reynolds numbers. So in between you're shearing the fluid very high, your particle undergoes this very high shear, and some of these particles, like for example cells, you might actually shear them. That might be your intent to shear them because you might want to lyse the cell. But if you want to keep these things intact, you might not want to go this route because of these relatively high shear rates. So having gone from this very high velocities, and we're going to go to slightly lower velocities with capillary-driven microfluidics. And capillary-driven microfluidics, I think most of you have seen something like this before. And this is the prime example of capillary microfluidics.